Good morning all. This is Dr. D. Khalandar Basha, working as Associate Professor in Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to discuss the stepper motor and keyboard interface with 8051 microcontroller under the course Microprocessor and Microcontroller. The slides are prepared by referring the textbook, the 8051 microcontroller, authors Kenneth J. Ayala, publications English Learning. So first we will see the stepper motor interface with 8051. So a stepper motor is a brushless asynchronous electric motor that converts a digital pulses into mechanical shaft rotation. So every revolution of the stepper motor is divided into a discrete number of steps, and the motor must be sent a separate pulse for each step. So every stepper motor has a permanent magnetic rotor called the shaft surrounded by a stator. So stepper motors can be used in various applications such as robotics, robotic arm, disk drivers, dot matrix printers, and automatic door locking system. So selection of the stepper motor according to the step angle depends upon the application. So the number of steps required to complete one rotation is equal to 360 degrees divided by the step angle in degrees. So with the steps per second, the relation between RPM and steps per second is given by steps per impulses per second. That is RPM into steps divided by revolution divided by 60. The figure shows the interfacing of a stepper motor to the microcontroller. So where the microcontroller is connected the stepper motor using 8255, which is programmable peripheral interface, through which the pulses will be sent to the stepper motor. So this is the excitation table for the windings, whether we can go for a clockwise rotation or anti-clockwise rotation. So for clockwise rotation, we can give the pulses either single winding excitation or double winding excitation. So in this example, we are taking double winding excitation. So in each windings, two windings will be excited. For the next clock pulse, B and C will be excited. For the next clock pulses, C and D will be excited. So after that, A and D will be excited. Once this rotation is done, again it will be go to excitation of A and B, followed by B and C, followed by C and D, followed by D and A. Whereas for anti-clockwise rotation, if you give the excitation first initially for AB windings for anti-clockwise, so the next iteration, the clock pulses are given for winding A and winding D, next winding C and winding D, followed by winding B and winding C. After that, this is a continuous pattern it is going to be. So the program for a stepper motor winding is move the data which is given for R7, next decrement R7, then again go to the loop 1, then R8. So this is a program for a delay. So after each rotation, how much time we want to wait, that will be given on this program to provide a delay. So here, what is the data we want to store here, or what is the data we want to load into D7 for providing the delay. So let X be our data, which we are going to be loaded to R7. So as in 8051 microcontroller, the clock frequency is given as 11.0592 MHz divided by 12. So the clock time period is given as 12 divided by 11.059 MHz, which is 1.085 microseconds. The number of clock pulses required to execute the loop, where we can say this move R7 comma data will be executed for 2 mission cycles, whereas DJNZ it requires 2 mission cycles, and this is a iterative, so this will be executed for X number of times, whereas RET instruction will require 1 mission cycle, so the total number of clock pulses are required is 2 plus 2 into X times plus 1. So this is the total number of clock pulses are required for executing the delay loop. The number of clock pulses required to execute the loop is 2 into 2x plus 1. For each clock pulse, the duration is 1.085 microseconds. So therefore, if we want to provide a delay of 500 microseconds, we will equate this time period to the 500 microseconds, which will use as 2 plus 2x plus 1 into 1.085 microseconds is equal to 500 microseconds. From that, x we will get as 229. So where this 229 will be loaded into the data, which indirectly will be loaded into R7. So if we are loaded the R7 with the 229 and this program, if we execute, it is going to provide a delay of 500 microseconds. Next, for rotating the stepper motor, we want to load some pattern here. This pattern we can write as ABCD excitation as 1100, so which is CC. For exciting starting as a BC, we are going to load the data is 66. So if you are giving the excitation initially for CD, the excitation pulse we have to give is 33H initially. If you are giving A and D as excitation, then we have to load with 99H. So first we will load any one of this pattern into accumulator by using the instruction move A comma hash some pattern, either it may be CCH or 66H or 33H or 99. As the stepper motor is connected to port 1, so this accumulator contents will be moved to the port 1. For generating the next pattern, we are going to rotate towards a right side clockwise rotation. So for this, we are going to use RRA. The accumulator contents, which is 66, will be rotated towards the right side by 1 bit. After rotation, we are going to send the accumulator content again to the port 1. After each and every clock pulse, we are going to provide some delay. So for a delay subroutine to call, we use the instruction A call delay. So when this instruction is executed, the control will be transferred to the delay program, where the delay program is wrote for 500 microseconds. So after executing this delay program, then the last instruction, which is RET, then it will come back to the next instruction, which is jump main. So it is going to continuously repeat it. So this is the program for stepper motor rotating in clockwise rotations. Next, we want to rotate in anti-clockwise rotation, means instead of RR, we can go for RM. Next, if you want to limit how many number of rotations we want, we are going to be load the number of rotations required into R1. After every pulse is sent, then we are going to decrement R1. So in the previous program, this instruction was not there, this instruction was not there, where it is going to generate infinite flow. So for limit the number of rotations, so how many rotations we require, the value we are going to be loaded into R1. After each pulse, the R1 count will be decremented. If it is non-zero, go to loop 1 for the next iteration. So next we will see the keyboard interface for 8051 microcontroller. So keyboards are organized in a matrix of rows and columns, where each row and column interaction is going to give one key. So the CPU accesses both rows and columns through the ports. Therefore, with the two 8-bit ports, the 8x8 matrix of keys can be connected to a microprocessor. So when a key is pressed, then the row and column makes the row value as well as the column values will make a contact. Otherwise, there is no connection between the row and column. If this key is not pressed, then this row and column will not be get interrupted. So whenever any key is pressed, the row and column will get into contact. So whenever this key is pressed, so these two will get contact. When key is not pressed, the key is left as open. So when no key is pressed, so the row and column will not be in contact. So in IBM PC keyboards, a single microcontroller takes care of hardware and software interface. So now we will see the example for a 4x4 matrix pattern keypad. The forecast flow matrix is connected through two ports. One is for rows, another one is for columns. So the rows are connected to a output port, whereas the columns are connected to input port. So now the row 0 we are going to be mapped to D0 of port 1, D1 of port 1 to second row, D2 of port 1 to third row, fourth row is connected to D3 of port 2. Similarly, to read the columns, the rightmost column you can read on D0 of port 2, D1 of port 2 will goes the second column, the third column is on D2 bit of port 2, the fourth column will be used on D3 of port 1. So when no keys is pressed, reading the input port will yields 1. So whenever it is connecting, so for initially we will make all the rows are grounded. So when the rows are grounded, so we are going to be write all the rows as 0. If the switch is not connected, then this column, as this switch is open, as this switch is open, this switch is open, this switch is open. So this row and the columns will not be get into contact. So the column line will be connected to VCC, which is going to give us logic block. So when we read the port 2, if the particular port bit is 1, it indicates no key were pressed. If it is reading as 0, indicates some key is pressed. So this is the logic behind for keypad interfacing. So if no key has been pressed, reading the input port will be equals to 1 for all the columns, since they are connected to VCC, which is active. So it is the function of the microcontroller to scan the keyboard continuously to detect and identify the key pressed. So to detect the key is pressed, the microcontroller ground all the rows by providing a 0 to the output latch, then it reads the columns. So if the data read from the columns, that is D3 to D0 of port 2 as 1, 1, 1, 1. For the 4 columns, if it is read as 1, 1, 1, 1, that indicates no key has been pressed. If one of the column bit has read as 0, this means the key corresponding to that particular column has been pressed. For example, if D3 to D0 is equivalent to 1101, so that indicates here we have one entry as 0, which indicates the keys which are there in the D1 column, that keys will be pressed. So after detecting the key is pressed, the microcontroller will go through the process of identifying the key. So starting with the top row, the microcontroller grounds it providing yellow and only for D0. It reads the columns. If the data read all are 1, that indicates no key is pressed in the first row. If grounds the next row, reads the column, then it check for any zeros. So this process continues until a row is identified. So after identification of the row, which is the key has been pressed, find out which column key has been pressed. So from the figure, identify the row and column for the pressed for following cases. If D3 D0 is equivalent to 1110 for the row and D3 D0 is equivalent to 1011 for the column. So here the column values as 1011. So that indicates the keys which are presented or which are connected to D2 has been pressed. So either key 2 or key 6 or key A or key E is pressed. For identifying this, so first we will make D0 0 and the remaining bits as 1. Again we will read the columns. If it is gives as 1111, indicates the key 2 is not pressed. Here we are given the pattern for the columns is rows is 1110. That means 1, 1, 1, 1, 0. As the columns are read as 1, 0, 1, 1, the key which is corresponding to D3 as well as D2, which is nothing but the key E is pressed. Second case, D3, D0 is 1, 1, 0, 1 for the row, that is 1, this is 1, right? 1, 1, 0, 1. So previous case also once again check. So D3 is 1, D2 is 1, D1 is 1, D0 is 0. And columns are read as 1, 1, 0, 1. So here the key 1 is pressed for the first case. Whereas for the second case, the values for D3, D0 is 1, 1, 0, 1. And columns are read as 0, 1, 1, 1, which indicates the D1 row and D3 row corresponding key, that is key 7 is pressed. So from the figure, the rows and columns can be used to identify the key. The row belongs to D0 and the column belongs to D2. Therefore, key 2 is pressed. Whereas the second case, D1 is row and D3 is column, which is the key 7 is pressed. Now we will see the program for detection and identification of the key activation using the following step. In the step 1, to make sure that the proceeding key has been released, the zeros to output to all the rows at once. So, and columns are read and checked repeatedly until all the columns are high. So, when the columns are found to be high, that indicates the program wait for a short amount of time before it goes to the next stage of waiting for a key is pressed. To see if any key is pressed, the columns are scanned over and over in an infinite loop until one of them has been read as 0 and the remaining columns as 1. So remember that the output latches connected to the row still they have the initial values as zeros only, making them grounded. So after the key is detected, wait for some amount of time around 20 milliseconds, which will call as key debounce, and then scans for each column again. So it ensures that the first key press detection not erroneous, one due to spike noise. Second point, the key is pressed if after 20 milliseconds of the delay, the key is still pressed, it goes back into the loop to detect the real key pressed. So detect which row key presses belongs to. It grounds one row at a time. Read the columns each at a time. If it finds all the columns are high, this means no key is pressed in the particular row. Therefore, it grounds the next row and continues until it finds a key is pressed belongs to. And upon finding the key, the row is belongs to, it set the starting address for the lookup table holding the scan codes for ASCII value for the particular. So to identify the key is pressed, it rotates the column bits one bit at a time into the carry flag and check to see if it is low. Upon finding the 0, it pulls to the ASCII value code for the key from the lookup table. Otherwise, it increments the pointers to point to the next element of the lookup table. So now here we will see the program for keyboard. This program sends the ASCII for the key which is pressed through port 0.1 and port 1.0 to 1.3 connected to rows, and columns are connected from P2.0 to P2.3, which is a 4x4 keypad. So first, to make the port 2 as input port, we will pass FF2 port 2 by using the instruction move P2, #0 FFH. If any value is starting with alphabet, receive that only 0. Next, to clear all the rows, we will move 0 to port 1 to make ground the rows of the keypad. Next, move A comma P2. This is for reading the columns. So port 2 values are read into accumulator. As we are connected, D0, D1, D2, D3 bits of port 2, we want to check whether these bits are ones or zeros. If all these bits as 1111, it indicates no key was pressed. So for checking it, we will add the accumulator content with 0FH or 00001111 in binary format. This is for checking from D0 to D3 bits. Suppose if the accumulator contents are, whenever we are ANDing with 1111, we will compare the accumulator with the pattern 00001111. So when these two are equal, that indicates no key was pressed. So again we go for repeating the same step. So this loop will be iterated, the key1 loop, until any key is pressed. If any key is pressed, this condition will not satisfy, it will come to the next. So first, once we know that the key is pressed, when this condition is fails, then it will come to the next instruction. So A call delay. It is for calling a key debounce. Then we will read the port 2 accumulator. We will AND the accumulator contents with 111B. Again we will compare whether these values are not equal or not. So compare, jump if not equal to the label over. Otherwise, next instruction, it will be go to key 2. As we know the key is pressed, we will call a delay for debounce time. Then again we are going to read the values of port 2. We will compare these values with 1111. So whenever these two are done, if key is pressed, so we go for finding a row. Otherwise, we go for keep on polling. So when it comes to over 1, we will make the port 1 by making D0 bit as 0 and the remaining bits as 1. That means here we are enabling only row 0. Then we will read the port 2, that is columns. Then again we will AND with the columns with the lower 4 bits, that is 0, D0, D1, D2, D3 with 111. Upper bits as however it is 0, don't guess. So if AND with this, again we are going to compare accumulator content with 1111. So whenever we have indicates, so if these two are not equal, that indicates a key corresponding to row 0 will be highlighted. Next, if row 0 is not pressed, then we are going to check for row 1, read the columns, and with 0FH, compare again. If these two are not equal, that indicates a row corresponding to row 1 is pressed. Suppose if key is not pressed, then we go for grounding D2 bit of port 0, port 1. Then we read the columns. Then again we will extract the lower 4 bits D0, D1, D2, D3. We will compare with these two. So if the accumulator contents are not equivalent to this, it indicates one of the key corresponding to row 2 is pressed. Suppose if it fails, then we will make the last row as 0. We will read the columns and we will AND with 00001111. Then we will compare accumulator with the 1111. So then if it is not pressed, then this condition is fails, then it will be go to K2. Otherwise, row 3 label will be executed. So at row 0, so when now row 0 is a key corresponding to row 0 is pressed, this block will be executed. If the key corresponding to row 1 is pressed, this key will be executed. So let us assume if a key corresponding to row 0 is executed, then the control will be transferred to row 0 label, where we are going to be load the address of the code for corresponding to 0th row will be loaded into DPTR. Then we go for finding out which key is pressed. Similarly for row 1, row 2 and row 3. Say once one of the key is pressed, then it comes to the label find. Then whatever the columns which you are read, which are in the accumulator, now we will rotate this one towards the right side by 1 bit along with the carry. So when J and C, when there is no key is pressed or carry is equivalent to 0, then we are going to get ASCII code. Then we go for incrementing the DPTR. Then again loop to find. If any match is fine, the accumulator contents will be cleared. Then the code corresponding to the particular key which is at accumulator plus DPTR will be loaded into accumulator. So where we are going to be fetch the ASCII equivalent for the key which is pressed from the lookup table and it will be loaded into accumulator. So then once the key is identified, the ASCII equivalent of the code will be loaded into port 0. For the next key pressed, we go for long jump to the K1, where K1 is given for the first instructions block, where we will make all the rows as 0, then reading the columns. So this will be a continuous iteration will be takes place. Next, ASCII lookup table, we have loaded into some address 3000H. In code 0, 0, 1, 2, 3 is loaded for row 0. K code 1, then 4, 5, 6, 7 it is for row 1. Code 2, 8, 9, AB is loaded for row 2. K code 3, C, D, E, F, that is for row 3 is loaded and end. So this is the program for keyboard interfacing with 8051 microcontroller. So the program steps are, first we will make all the rows with zeros. Then we will read all the columns. If columns are given as 1111, it indicates no key was pressed. If any one of the column values is 0, then one of the key corresponding to this particular column is pressed. So for identifying which key is pressed, the row values first it will be given for 0 and the remaining values as kept as 1. Again we will read the columns. If this key is not pressed, it is going to read 1 and the remaining bits also 1. So we will end with 000 1111 with accumulator contents and we will compare with 0FH. If these two are equal, indicates this row key is not pressed. Then we will make the next column as 1. The next row is equivalent to 0. Again, we will read the columns. We will end with 1111, the lower 4 bits of accumulator. Then we will compare with 0FH. Again, if it is given the same value, that indicates none of the key corresponding to the row will be pressed. If these two are not equal, if the pattern after ending is not equivalent to 00001111, indicates one of the key which is in tag with this row and this column. This key is highlighted, indicating the particular key was pressed. So this we are going to be loaded into port 0. So in this session, we have discussed the interfacing of stepper motor and a keypad, which is a 4x4 keypad interface with 8051 microcontroller. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.